Welcome back. We are now evolving into a really, really important section of a concept in calculus that we use quite a bit, and that concept is what we refer to as continuity. And so we're going to start that idea of continuity with two different graphs. There are many different types of functions, smooth ones and ones that have breaks or jumps in them. Breaks or jumps. No typo, sorry about that. Or jumps in them. Now, one graph models the length of a fish T years after it is hatched, and the other graph represents the cost of parking in T minutes when a quarter is equivalent to 15 minutes of parking, let's say in a parking meter, okay? So if you look at each one of these, hopefully the length of a fish does not jump from one length to the other. Notice here, you can hopefully kind of see according to labels that this is the one that is describing the fish, and this is the parking meter one, let's say. And notice on the left we have a nice smooth curve because we grow in a nice smooth fashion. The lengths kind of continue off. Then we end up having some jumps here. Here's 15 minutes for a first quarter, 15 more minutes for another quarter, 15 more minutes for a third quarter, etc., etc. So it's a constant rate whenever we are within a 15-minute increment. So here, this is what we say is a continuous function. And this is a continuous function only in between where we are smooth or constant, okay? So like at x equaling 15 or t equaling 15, t equaling 30, t equaling 45, we would have a function that is discontinuous at that point, okay? So having a smooth curve is important in aspects of calculus. Therefore, one must determine the continuity of a function in many cases. So here's kind of a checklist, is what your book calls it a checklist. I've called it the definition of continuity before. But in order for f to be continuous at some value of a, then the following three conditions must hold. So, first one, f of a has to exist. F of a exists, so you get an actual value. You have a point at a, and that's going to make that exist. Number two, the limit as x approaches a of that function also exists. So, what does that mean? That means that when we go back to the idea of our two-sided limit, that you have to double check and make sure that the limit from the left and the limit from the right are the same value, hence making that limit as x approaches a of f of x existing. Now, if both of those exist, and number three, the limit as x approaches a of f of x equals that f of a, so the number you get in number one and the number you get in number two are exactly the same, hence our function is continuous at a. So, if one or more of those conditions fail to hold at a, then f is discontinuous, if I can spell it, discontinuous at a. Okay? So, if number one does not exist, you don't have to check anymore. Okay? It's all the way done. It is discontinuous. Once one of those fails to hold, obviously, if that fails, number one fails to exist, number two could exist, but then number three is going to fail again, that the limit does not equal the non-existing function value. Okay? All right, so let's look at this graph, and we're going to talk about some of these values between 0 and 7. We have to identify the values of x at which we are discontinuous. So I'm hoping you can kind of see in this function, being discontinuous means you have to kind of like drop or stop and pick up your pencil and start again, and pick up my pencil and put that point and start again here, picking up our pencil, etc. So those are some good places to kind of think about for discontinuity. Now, we're from 0 to 7, not including the endpoint. So I'm not even going to start at x equals 0. I'm going to start at x equaling 1. For x equaling 1, I need to check those three conditions. So the number one is, what is f of 1? If I look along x equaling 1, and I look for f of 1, that is where the function value is existing. That's the dot or the line that goes through there, symbolizing kind of a dot. Notice here I just have an open circle. Therefore, this does not exist. So right here we can kind of stop and say, well, here at x equaling 1, because the function value doesn't exist, then we're not going to be continuous. But let's kind of look at all aspects of this because on your My Math Lab, it may ask you to kind of check each one that holds true or doesn't hold true. So if we ask about the limit under number 2 condition, around here that function from the left is going to 3 and from the right is honing in at 3. So we're honing in right here on that open circle. Therefore, the limit does exist when x equals 1. It's equal to 3. But number 3 does not hold true. The limit as x approaches 1 of my function is not equal to f of 1 because f of 1 doesn't even exist. Okay? So x equaling 1 is discontinuous. All right, let's look when x equals, what's the next one? Here's 2. Oh, looks like I have a break there. What happens when x equals 2? Well, let's look at f of 2. Where is the dot? Where is it cross through? And I look at x equaling 2. Ah, right there is a dot. So right here, f of 2 is equal to 3. Mentally looking as I approach 2 of that f of x, what that limit is equal to. So from the left, I'm coming down to 1. From the right, I'm coming down to 1. Honing around that open circle from both sides. Therefore, my limit equals 1. So each one of those exists this time, but the reason that we are discontinuous as we approach 2 is because this limit does not equal f of 2. 3 does not equal 1. Therefore, we are not continuous at x equaling 2. All right, so there's x equaling 2. Let's move over to x equaling 3. Notice here, whoop, I've got a little jump right there. So let's look at x equaling 3. Which of our conditions does not hold true to make that discontinuous at x equaling 3? So let's look at f of 3. f of 3, where's that dot? Where's the solid dot? It's right there when y equals 1. So f of 3 equals 1. Let's look at number 2. That should be a 2, not a 3. The limit as I approach 3 of my function. So, what do I know? So I approach 3 from the left, I'm at y equaling 2. If I approach 3 from the right, I'm at y equaling 1. Because there's this jump, the limit from the left does not equal the limit from the right. Therefore, that limit does not exist. And hence, if we check number 3, the limit that does not exist as we approach 3 is definitely not equal to that function value at 3. So, making sure that you end up having each one of those conditions hold true and that the 1 and the 2 have to equal for it to all be continuous. All right, let's look. There's x equaling 3. Look at x equaling 4. 4, there's no open circle, nice smooth curve through x equaling 4. That's going to be continuous on that nice smooth curve right there. So we're not going to check x equaling 4. The next one I'm going to look at here is x equaling 5. So if I look at the first condition, does the function value at x equaling 5 exist? Well, that dashed line right there symbolizes a vertical asymptote. Therefore, this does not exist. Okay, number 2. If my lab math continues by asking you about the limit as x approaches 5 of that function, what do we know? Well, from the left of 5, if we look on our graph, our function's going up, 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 we'd say to positive infinity. To the right of 5, as it comes in from the right, we go up, 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 we would say to positive infinity. Since those are the same, we symbolize that it goes to positive infinity around that asymptote. But recall, this still means that this limit does not exist. So that is a DNE. So obviously, 3 is not going to hold true either, okay? We're just going to say they are non-existing, okay, or whatever the case may be. So, hence, because 1 and 2 are do not exist, excuse me, because these do not exist, hence we are discontinuous at x equaling 5. So, they may ask you for intervals of continuity. The only breaks that we have here at 1, 2, 3, and 5, everything else has a nice smooth curve around it. So we're continuous at everything around those other values except for at 1, at 2, at 3, and at 5. So remember, we're on the interval from 0 to 7. So intervals of continuity is going to look like this. I'm going to be continuous from 0 to my first discontinuity, which is x equaling 1. Then I'm going to skip from 1 to 2 with a nice smooth curve. We are continuous from 1 to 2. Union. We are then going to start from 2. Everything from 2 to 3 is a nice smooth curve, so it's going to be continuous from 2 to 3. From 3, we can skip over 4. We're continuous through there, but we have an asymptote at 5, so we're not equal to 5. You can't hold that in there, so 3 to 5. And the last one will be from 5 and ending at 7. Notice we're not including 7. We're not including 0 at the beginning, so therefore these two, that's a parenthesis and that's a parenthesis as well. Okay? Now, the reason we do that also is because we haven't talked about limits from the right or the left and continuity, which is coming up. So, the discontinuities, talk about what we named them, and I'm not going to be too picky on these that you know them, but I want you to be aware of them. The continuities at x equaling 1 and x equaling 2 are what we call removable. The R didn't take. Removable discontinuities. And the reason that we call them removable is because if I come back to my picture, if I were to define the point f of 1 equals 3, that would close that circle up and it would then be continuous. So I can remove the continuity or the discontinuity there. If I redefine this point at f of 2 equaling 3 to make it f of 2 equaling 1 and basically just move it down here, I would have removed the discontinuity by redefining a point. Okay, so that gives us removable. But the discontinuity at x equaling 3, there's no way just to remove that discontinuity by filling in a point. We actually have a jump in our graph there, and that's hence the name. We have a jump discontinuity because there is a jump in that function. And finally, the discontinuity at x equaling 5 is because I have that asymptote there, and what mathematicians refer to that is an infinite discontinuity because of that asymptote. Okay, so very, very important to know what's in that box right there. That f of a has to exist, the limit has to exist, and they have to be equal in order for our function to be continuous. So let's go from a graph to actually looking at some functions and determine if we are continuous at the value of a. Justify each answer using the continuity checklist. So if we look here for the first value, or the first checklist part, we are looking at what is f of 1. Well, if I try to put 1 in there, 3 times 1 squared plus 2 times 1 plus 1 all over 1 minus 1. Well, the top, I don't really care what to figure it out, but we will. 3 times 1 squared plus 2 times 1 plus 1, so I get 3 plus 2, which is 5, plus 1, which is 6. Now, why did I not care? I didn't care because look at the bottom. I have a 1 minus 1, which is a 0. Is that a valid answer? Is that going to exist? The answer is no. This is do not exist because it's a rational function that is looking at the value around where it is not equal to in the domain to make it equal to 0. So remember, x equaling 1 here would not even be a choice in the domain of this function. So, no. Therefore, f of x is not continuous at x equaling 1. Okay, that's my conclusion there. But if I have the same function and I change my a value, am I going to be continuous at a equaling 2? Well, let's check. Let's look what f of 2 is. Again, taking 2, plugging it into my function, I get 3 times 2 squared, which is 12, plus 2 times 2, which is 4. So 12 plus 4 is 16 plus 1, which gives me a 17, all over, in both cases, plug 2 in the bottom, 2 minus 1, which is 1, and that gives me 17. So basically, I plug 2 in to that function. I get a number out, so it exists. What happens now when I look at the limit as I approach 2 of my function? Well, what's the first rule of limits? Plug that into your function. Well, I just plugged that into my function here. I'm going to get the same answer out. So I'm just going to save me a little bit of work and know that that's going to equal 17. And the third checklist means that I need to evaluate, is this number equal to that number? Well, all day long, 17 equals 17. So therefore, as I approach 2 of f of x, that is equal to f of 2. So therefore, those little 3 dots in a triangle mean therefore, f of x is continuous at x equaling 2, or when a equals 2. X and a, same thing. A is an x value. Okay? All right. Moving right along, let's turn ourselves to a piecewise function. Actually, 2 piecewise functions here. And look at our 3 conditions of our checklist. The first one being, what is, in this case, f of 3? I'm looking around a equaling 3 here. Well, where is x equaling 3? Right here. What's the y value? It is 4. So by the piecewise function that tells you that, it gives that to you. The second condition, I need to look at the limit as x approaches 3 of x squared minus 4x plus 3 all over x minus 3. So I have to determine, can I plug 3 in? Well, the answer is no, because in the bottom I get a 0. In the top I get 9 minus 12 when I multiply 4 times 3 plus 3 gives me 0 over 0. Hence, when we have 0 over 0, we must end up trying to factor the top, is what I would try first. So if I factor that top, I get an x minus 1 and an x minus 3. Therefore, this and this cancels. So I'm looking at the limit as x approaches 3 of x minus 1. Now plug 3 in, and I get the value of 2. But that's not very nice when I want it to be continuous, possibly, because the limit that I find as x approaches 3 of my function in step 2, this does not equal that. So that's not equal to f of 3. Therefore, we are not continuous at x equaling 3. Now, is it possible that we could be continuous in other places? Absolutely. But we were just looking at when a equals 3. We didn't need to go further than that. We will get there. Okay, let's look at this piecewise function. Again, x equaling 3, we have 2 linear functions here. First off, I want to look for f of 3. So this time I'm honing in on the inequality up here that has the equals, which is right here. So I'm going to plug 3 in there. So I get 2 times 3 minus 5, which is 6 minus 5, which gives me 1. Okay, that's the function value at 3. Now, if I want to look at the limit value around x equaling 3, notice that's the breakpoint of this piecewise function. So that means I'm going to have to determine whether or not the limit exists by evaluating the limit from the left and the limit from the right. So what is the limit as x approaches 3 from the right of f of x? And what is the limit as x approaches 3 from the left of f of x? That's what we need to determine. And that is all determined by our inequalities right here, okay? So x greater than or equal to 3, that means I'm to the right of 3. So coming in from the right of 3, I'm going to plug that in. And we did that. 2 times 3 minus 5 gives me a 1. And you can do this mentally or you can write it all out. If I now come from the left of 3, x less than 3 are all the numbers to the left of 3. If I plug 3 in there and subtract 4, I get a negative 1. So therefore, are these two one-sided limits equal? Absolutely not. Therefore, the limit as x approaches 3 of f of x does not exist. And we can stop right there, because if that doesn't exist, that means that I'm not continuous at that point. So, therefore, f, make that an f. F is not continuous at x equaling 3. Okay? All right. Very, very, very good. So we only found one of those 4 functions that were continuous at the value that we were looking for. Okay? All right. So now let's turn our attention to some theorems, because not all the time are you going to have to check the continuity of every single point. That would just be ridiculous. But if we have some theorems that talk about the continuity of a function, then we can use this theorem when we are being asked whether or not things are continuous. So you have to be able to know these theorems and know them well to be able to use them in other aspects. And we will see that aspect here in just a little bit with the intermediate value theorem. So for theorems of continuity, f and g are continuous at A, then the following functions are also continuous at A, and we're going to assume that c is a constant and n is greater than 0 is an integer. So if f and g are continuous at A, then the sum of f and g are continuous at A. The difference of those are continuous. Taking a multiplier times that function is also continuous. Multiplying the two functions together would yield a continuous function. Dividing the two functions together would yield a continuous function as long as g is not equal to 0. And the last is if I take a function to a power, that new function would also be continuous as well. So, sums and differences, quotients and products, all of those are going to be continuous. Now, these are the ones that you really, really want to make sure you remember. Okay, these are going to save us some time, especially kind of part A and part B. So, we look at a polynomial. It's a nice smooth curve, bounce, 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 maybe go down something like this. Where is it continuous? Well, I can draw any polynomial function without picking my pencil up. Therefore, over its domain, which is all real numbers, that function will be continuous. Okay? A rational function will be continuous everywhere in its domain. So a rational function is a fraction where we are going to be looking at all reals except where the denominator equals 0. So you look at where it equals to 0, you take that out. It's not going to be continuous at that spot, but it will be continuous any other place in that domain. Now, trig functions. We're going to look at sine of x and cosine of x. Those are our nice cyclic functions that look like this. So therefore, its domain is going to be all real numbers for any sine or cosine function. But the other four, their domains are specific to the function. Okay? So in each one of those functions, you're going to have some asymptotes. The domain is equal to all reals except the vertical asymptotes. So exclude all of those values where you have an asymptote. Now, a radical function, I'm looking at a radical function as the square root of x. Okay, or the nth root, excuse me, not the square root, the nth root of x. It would be the square root of n equals 2, which we're going to delineate these two by whether that n on the outside is odd or even. So if we have an odd index on the outside, the cube root of 8, the cube root of negative 64, the fifth root of negative 1, all of that kind of stuff, you can take the radical of each one of those. So therefore, our domain of any nth root that is odd will be all real numbers. But if it is even, take the square root of something, the fourth root of something. Remember, that can't happen on negative numbers. So our x value has to be greater than 0 for that domain. That is the domain. The x underneath would be whatever the radicand is underneath, where that is greater than 0. All right, so let's determine some intervals knowing this. Determine the intervals on which the following functions are continuous. So you have to know what kind of functions these are to be able to lock into place which of these is going to help you. So this is a fraction. That's a fancy for our rational functions. And we're going to be looking at being continuous in all real numbers except for where the denominator equals 0. So if I want to know where x squared minus 1 equals 0, you can solve that equation. I would recommend you go ahead and kind of factor that if you want. That would be a difference of squares is an x minus 1 and an x plus 1. And where is that going to be 0? Well, what makes this 0 is 1. What makes this 0 is negative 1. So that means that that rational function is defined for every single number except for 1 and negative 1. This theorem tells me it would be continuous at every single one of those numbers except for 1 and negative 1. Therefore, my intervals are going to be, so if you need to look at a graph or something and you want to skip over negative 1 and 1, open circle, and I need all of this, and I need all of this, then do so if you need to write it with your interval notation. So I'm going to go from negative infinity to negative 1. Then I'm going to skip from over negative 1 and go negative 1 to 1. Then I'm going to skip over 1 and go from 1 to infinity. So it's a union of 3 intervals here. Looks like 3 ordered pairs, but remember that's interval notation, therefore it is representing those numbers between those. All right, next example. What kind of function do I have here? 2x to the 4th minus 3x cubed plus 5x minus 1. That is a nice smooth polynomial. Has a power of 4. So it ended up doing something like this where I bounce around and I go back up. And so we end up having, according to this theorem, where is our function continuous? It's going to be in all real numbers. So I'm going to go from negative infinity to positive infinity as my interval of continuous points. So you may want to write, what kind of function that you have here so that you remember. This is a rational function. So maybe draw an arrow up or something like that to that rational function. But that's going to give us some easy ways to get away from checking those 3 steps every single time. All right, let's move on. A function is said to be continuous on an interval if it's continuous at every point in that interval. So that means that I'm not including the endpoints. Now, what if we want to include some of those endpoints? Then we have to evolve into what we refer to as left and right continuity. So I'm going to have some a and some b, and I have some function that is defined at a, it's decreasing, it's open here at b. And notice it's nice and smooth in between, but I actually have a value that is an f of a in this case, where I actually have a point on that. So here we would refer to this as right continuous on, now I'm going to include a but not include b. So I need a closed bracket and then a parenthesis around b. Another type of function, maybe an a and b, that I have, I'm going to open circle here, I'm going to decrease, I'm going to be defined by f of b here by a solid dot. So here, now I know it's on the right hand side, but we call this left continuous because we are approaching on our limit from the left. So this is, it's kind of backwards. Left continuous on, now not including a, but including b this time. So those are the types of things that we're going to include and also kind of check when we're working with continuity at endpoints and checking some of those endpoints. So we can use our theorems to talk about the majority of the values being continuous on the domain, but here we have to use left and right continuity in order to combine the endpoint in on that. So a function f is continuous from the right, or what we refer to as right continuous, at a if the limit as x approaches a from the right of f of x equals f of a. Okay, so we take away where it's just a two-sided limit. Now we bring in this plus in this case on the right continuous to determine that endpoint is included or not. And f is continuous from the left or left continuous at a if the limit as x approaches a from the left of f of x is equal to that function value at a. So it kind of looks like the last step of the 3-step checklist to determine whether or not we have continuity from the right or from the left. Now, if we have continuity on an interval, a function f is continuous on some interval I if it is continuous at all points of I. So again, on that interval, a lot of times we can use those theorems to decide that. And if I contains its endpoints, then the continuity on I means continuous from the right or from the left at the endpoint. So again, majority of things comes from the theorem on the inside here. We have to check the endpoints as well. So let's try this problem here. We need to complete. Part A says that we want to use the continuity checklist to show that f is not continuous at the given value of a. okay? And if it is not continuous, then we're going to determine whether f is continuous from the left or from the right of A, and then we're going to state the intervals of continuity. All right, let's see if we can put a graph on this. If I put a graph on this, this is a parabola where it's moved up 1, and I only want the left-hand side where x is less than 1. Now, notice I have an equals there, so at 0, 0 squared plus 1 would be at 1. So I would end up with kind of my half of my U shape here going this way. And if I have a line where I'm up 1, 2, 3, 4, 5 on the intercept, it means I go up 1, 2, 3 over 1 to get my next point. I am not equal at that point, so I'd have an open circle here going in that direction. So it almost looks like we're going to be on a right-hand side continuity because we're coming in from the right on this endpoint right here, okay? So let's determine our checklist. So part 1, let's look around 0, okay? That's the only part that's in question here. So if I look at f of 0, what is that equal to? Well, I go to the equals and I plug 0 in. So 0 squared plus 1 is 1. For my graph, I symbolize that by that solid dot. If I then look at number 2 on my checklist, what is the limit as x approaches 0 from the right of f of x? And what is the limit as x approaches 0 from the left of f of x? If these are the same, then that limit exists. So if I look at 0 from the right, so coming in from the right, I'm honing in around that x or y equaling 5, excuse me. And if I'm coming from the left, I'm coming down here to y equaling 1. Therefore, the limit as x approaches 0 of f of x does not exist. Now, I can stop at that point. Therefore, f is not continuous at x equaling 0. Check. Part A. I figured it out. We are not continuous at x equaling 0. And so then, I now need to part B, determine whether f is continuous from the left or from the right of A. Well, we can kind of have our work here with us here, okay? Sorry. I think I said it backwards earlier, okay? So we're coming from the left. I said it was on the right-hand side, but remember it's opposite, so I already confused myself. We're coming in from the left of 0. Notice that the limit, the one-sided limit here is equal to this. Therefore, by our definition above, we can determine that we have left continuity in this case. So, part B, since the limit as x approaches 0 from the left of f of x equals f of 0, then sorry for the delay, then f is continuous from the left at x equaling 0. Okay, so coming in from the left, as I approach 0 from the left, that is equal to the function value that we found in part 1, or part A. So part C says, once we know that, then we need to state the intervals of continuity. So from negative infinity all the way up to 0 here, I'm going to include 0 on this side, but then I'm going to union from this side. From 0 to infinity, we have discontinuity. So we're not including that endpoint at that place. So we're going to go negative infinity to 0. Union 0 to infinity would be my interval of continuity. Okay? All right, very good. Next function. Determine the intervals on which the following functions are continuous. So, we need to determine whether we are continuous for this radical function, x squared minus 9. So if we go back to our theorems, and the radical function, when I have an even number out front, I am going to be continuous on all the intervals where x squared minus 9 is greater than 0. Okay? Now, you can do this inequality out. We've done it before. If you need some help on doing this again, please ask. X minus 3 and x plus 3, I would end up on my intervals. I would have zeros at 3 and negative 3. But if you also want to kind of look at a picture of this, this is kind of half of what we call a hyperbola. So it's going to end up having this going in this direction, and then I have this going in that direction. It's kind of the reverse of a semicircle. If it was 9 minus x squared, I have a semicircle here. All right, so because I know this is true, I know from my theorem, because it's on its domain, the domain is from negative infinity to negative 3, greater or union the 3 to infinity. Now the question is, can I lock in the endpoints here? And that's where we have to check the limits from the left and the limits from the right. So let's look at number 1 of our checklist. What is f of negative 3? Well, if I plug negative 3 into this function, square it, subtract 9, I get a 0 after square rooting it. If I look at number 2, what's the limit as I approach negative 3? Now, which way am I coming from? I'm coming from the left on this function, negative 3 from the left of f of x. Well, what do? I plug in a into my function, and I still get a number, so I don't have to do anything to it. So I know that that's 0. Therefore, the limit as x approaches negative 3 from the left of f of x equals f of negative 3. Therefore, I am continuous at that endpoint of negative 3. So now I can determine that I can block this in with a bracket now versus just leaving it open. Now, what happens when I check around f of 3? F of 3, plug 3 into my function, and I go 3 squared minus 9 is 0, square root of that is still 0. Number 2, if I look at the limit as x approaches 3 of f of x equals 0. As well, because when I plug, from the right, let's say, I need to put a position on there from the right. So if I end up plugging 3 into here, squared minus 9 gives me 0, I get a valid number. Therefore, the limit as x approaches 3 from the right of f of x equals f of 3. And again, that allows me to say that that endpoint does have continuity at x equaling 3. Hence, the final interval that I can get from this function, I know it's a little bit long to have to write out, but from negative infinity to negative 3, including negative 3 with a bracket, union a bracket of 3 to infinity would also give me that continuous function. Okay? All right, very good. Now, let's look at f of x equaling x squared minus 2x plus 5 to the 2/3 power. Now, in disguise, this is a radical function of the cube root of x squared minus 2x plus 5, all of that squared. Okay? Now, the x squared minus 2x plus 5 is a polynomial that is continuous everywhere, but now it's under that cube root function. So please remember that because this is an odd index, or an odd down here for your root, then by our theorem, it says that our function is continuous everywhere, all in the real numbers. Okay? So that would mean that the interval that we are continuous on would be from negative infinity to positive infinity. And that's where it is. Okay? All right. Sorry for that delay again. All right. Very good. All right. So we're going to now get a theorem that is very, very important, kind of to yield some values for us. Mingled within this section, there will be some evaluating limit problems that you have. Just be aware of that. Just remember to plug A in, see if that gives you a value. If it gives you 0 over 0, factor or rationalize. But finally, we're going to discuss this important theorem, which is the intermediate value theorem. This theorem is worthwhile to determine whether a function has a solution. So let me give it to you and draw a graph and then we'll work with it. We're going to suppose that f is continuous on the closed interval AB and that L is a number strictly between f of A and f of B. Then the intermediate value theorem states that there is at least one number, call it C, in the open interval of AB satisfying f of C equaling L. So, what does all that gibberish mean graphically? I'm going to kind of do a graph here. I'm going to start with A here and B here. That's my interval. I'm going to have an increasing function where I have a point there and a point here. Now, this over here, if I plug that into my function, this we could write as f of A. If I plug B into my function and get this point, then this f value would be whatever f of B is equal to. So what they are stating by the intermediate value theorem is that I would then have some L value on that's between f of A and f of B, such that if I come over here onto my function, I can guarantee that that C value is between A and B. So a lot of times we don't necessarily find this L value. A lot of times we're finding where the 0 is, so that's where you're finding kind of your intercepts. But it can work for any L value that you choose. So then if I draw also a graph, call this one A, call this one B, and I end up having a function, start with a point here, and I end up doing something like this, and come down to B. Same way, if I throw B in, then the matching Y value here is f of B. If I throw A into my function, then over here the matching Y value is f of A. Now, I'm going to choose some L value. I'm going to choose it right here that I can guarantee as long as L is between f of A and f of B, this theorem tells me that I can go across here and determine that there are a C value or at least one number. In this case, I'm going to have 1, 2, 3 intersections. So call them C1, C sub 2, and C sub 3. This is a case showing you that there could be more than one C value between A and B that satisfies this theorem. Okay? So, we're going to use the intermediate value theorem to determine, on the next page, maybe, if I can get it to change. All right, use the IVT to show that the equation has a solution on the given interval. Then use a graphing utility. I'm suggesting Desmos.com, or you can use a graphing calculator to find all the solutions to the equation on the interval. So on a test situation, I'm probably not going to make you find the solutions, but I would kind of maybe ask you to verify that this would exist, that there would be a C value existing, okay? All right, so here, our limit value is this. This is L, and this is our function value. So we're looking for when this function value is equal to -1 on the interval from -4 to 2. Now, we know that this is a polynomial function, so therefore f is continuous everywhere because it's a polynomial. Now, why is that important? Because the IVT says if f is a continuous function, if it's not a continuous function, it's not going to work. So we know that that's true. Now, I need to determine what is f of -4 and what is f of 2, because these are A and B. So, plugging that into my function, so that means that I got to do opposite of -4 cubed minus 2 times -4 squared plus 3 times -4. And I will tell you that if you do that, you will get the value of 20. Again, it's just evaluating functions. Again, putting 2 in for every x that I have in my function. If you multiply all that out, add or subtract, I will tell you that this is -10. So the question is L is -1 between f of A and f of B? Yes. Okay. So L equaling -1 is between f of -4 and f of 2. So by the IVT, there is at least one C between -4 and 2. So not until we look on our graph are we going to know how many of those that there are. Okay, so I'm going to have to go over to this computer and work on some things as I record. First, I need to expand off this. Okay, so I need to expand it off a little bit so you can see this website here. On this website, this is Desmos.com. Notice that you end up having a piece here that you can type in the function. So I'm going to type in y equals -x, and you can use this keyboard down here. I know it's out there. There's a little keyboard right there. Or you can use the caret key, the shift 6 to get the exponent. -x cubed minus 2x, shift 6 squared, or you can do the little square down here, plus a 3x. So there's my graph, but I'm going to hit enter to give me another one. I need to know where y equals -1. That limit, where's the -1 values for that function? So I'm going to set y equal -1 as this horizontal line. Now notice that as I sit here and I hover over these points, that I get some x values when y equals -1. And these right here are solutions for that function, okay? So these are the things that they're asking for in part B. What are the solutions, and give a graph. So if we go back here, the solutions that I have, and you can toggle back to your computer and stuff, but the solutions are -2.912, -0.286, and 1.199. Those are going to be the solutions that I have there for that. Let me move this. Trying to move this back. Oops. Okay. There we go. Okay, so those are our solutions, and you can just kind of sketch a graph there if you want. And you can pull it from that. On my lab math, I'm sure you're probably gonna, it was something that looked like this. And we ended up having those solutions here, here, and here at -1. So you're going to have to evaluate and kind of look at that graph. These points here that they show along the L value is going to be very, very important for you. Okay? All right. Last problem. Find A such that F is continuous. Well, we know that that function is going to be continuous everywhere except possibly at x equaling 2. Because that's the break point. It's continuous everywhere because each one of these are polynomials, except possibly here. So number 1, we need to determine what is f of 2. Well, where's the equals? The equals is right here. I'm going to take 2 and plug it in, so that means I got to do 3 times 2 plus 2. Well, 3 times 2 is 6 plus 2 gives me an 8. Second part of my checklist, the limit has to exist. So the limit, as x approaches 2 from the right of f of x, has to equal the limit as x approaches 2 from the left of f of x. So, here we are. If we look at x greater than or equal to 2, that's coming from the right. When I plug 2 in, times 3 plus 2 gives me an 8. But when I come from the left and I plug 2 in for x, I get 2 times a plus 16. So the best I can write is 2a plus 16. Now the whole idea of this exercise is to determine what a is, and how are we going to do that? We have to make sure that that limit exists. So we need to take whatever these two things are. For that limit to exist, they better be equal. So all I have to do now is set equal to each other and solve that two-step equation. So I get 2a equals -8, and a equals a -4. And that, ladies and gents, is our final answer. And that negative did not take. So x equaling -4 would be work. Okay? All right, very good. So we're going to go now from continuity to our last section in chapter 2, which actually brings in a very precise definition of limits. And that's kind of some mathematical terms behind the whole thing. It shouldn't be too bad, but it will be our last section in chapter 2. Until next time.